Hello, I'm Bhavesh. Welcome to our channel. We make educational videos here, and this is our first series.
Hello everyone. Today will be the first of many classes in our series of Introduction to Computer Science with Bhavesh Kumar. In this course, we'll be talking about computer science as a whole. We'll start the class by talking a bit about computer science, what it is, and how the computer actually represents information and how it represents all these beautiful things that we see on our computer screens these days. Then we'll dive deep into the vast world of Python. We'll be talking about some of Python's syntax, talking about branching, loops, and abstracting the idea of a computer science programming language to do various tasks that are above and beyond what a human can expect. Then we'll move on to a very important lecture, which is about data structures and algorithms. This lecture is important not only for this class, but it will be important in the future if you're ever trying to get a job. Then we'll dive deep into object-oriented programming, and we'll code our very own games for the first time and understand how very powerful the programming language of Python really is. So let's start talking about computer science by first defining what a computer is and how it relates to computer science. So a computer does two things and two things only. The first, it calculates and processes information that is given to it to produce an output, and it stores information inside of it. So relating that to the actual field of computer science would be the actual process of solving these problems. So it would be the black box in the middle, where the computer takes in input from users and other fields, and it uses computer science, logics, and other things, which is this black box for now, to take out an output. Before we actually talk about this black box, we first need to talk about representation. How does computer represent all this information that we see on the screen? Now, us humans, when we talk about representation, we talk about how we represent all these numbers and digits using something called the decimal representation system, where we take any three symbols, for example, the symbol 1, 2, and 3, and in our minds, we automatically tell ourselves that these three symbols equal 123. Now, if you went to kindergarten and learned the decimal system the same way I did, you would remember seeing this chart. To show you what I mean, in my head, we take these three symbols 1, 2, 3, and suddenly it represents the number 123 because we do quick arithmetics where we take 1 because it's in the hundreds place and multiply it with 100, and then we add it to 2 times 10 because it's in the tens place, plus 3 times 1 because it's in the ones place. And we add these together to represent the number 123. In this same way, we would go on to represent binary. If in decimal systems, since there are 10 symbols, 0 through 9, we represent each place value using a power of tens. So ones, tens, hundreds, thousands, 10,000s. This happens because in each place value, we can represent enough information with just one place value that we don't need to use the second place value. For example, we can go as high as 9 with only 1 because we have about 10 symbols. So we can only use 10 symbols in one place value. But in order to go from 9 to 10, we need to use another place value to ensure that this number actually represents the number 10. In this same way, binary uses values of 1, 2, 4, 8, it's 16, so on and so forth. So in binary, instead of the ones, tenths, and hundredths place, it uses the ones, seconds, and the fourths place because it only has two symbols. So this would represent 2 to the power of 0, 2 to the power of 1, so on and so forth. Because once we write 1 in here, representing the highest this one's place value can go, we have nowhere else but to go to the second place value. So we would represent 2 as 1, 0. In the same way we represented binary a minute ago this way, we represent decimal using the same arithmetic, where we multiply 2 times 1 plus 1 times 0 to represent the number 2. Now if you were to write the number 3, so this would equal 1, this would equal 2, this is decimals, this is binary. 3 would be something like 1, 1. We can see this as we multiply 1 times 1, that would equal 1, plus 2 times 1, which would equal 2. So this would represent the value of 3. The same way we would represent 4 as 1, 0, 0, 5 as 1, 0, 1, 6 as 1, 1, 0, 7 as 1, 1, 1, and since we have expressed all possible values with 3 place values and 2 symbols, we move on to the 8th unit, where we represent 8 as 1, 0, 0. Here are some practice problems that you can use to sharpen your skills of binary. For most of these binary problems, you can probably use the system I talked about. But to convert decimal into binary, there's a special secret and a special technique. For example, if we were to convert the number 55 into binary, we would use simple division to convert 55 into binary as quickly as possible. So the algorithm to do this goes something like this. You divide by 2, keep writing the remainder until the remainder equals either 0 or until the quotient equals either 0 or 1. So if we were to divide 55 by 2, we would get a remainder of 1. Sorry, this is 27. If we were to divide 27 by 2, we would get 1, 13. 2 is 1, take this with 6. Now here's the remainder 0, the quotient is 3. We'd go on, 1, just equals to 1, but even though we cannot divide it anymore, we can still write the remainder to be 1. So now if we traverse this, we get our answer of 1, 1, 0, 1, 1, 1, which equals 55. Now that we've represented any information into terms of binary, what do binary actually means into the physical world? Well, binary is a 2-digit system where 2 symbols, 0 and 1, true or false, on or off, electricity in or electricity out. The same way, we use something called transistors inside of our computer to represent many, many digits. You can think of a transistor like a light bulb. Imagine the light bulb turning on as it equaled 1 and the light bulb turning off as it equaled 0. So imagine that there are hundreds and thousands of tiny, tiny light bulbs, known as transistors, inside of our computer, which turn on and off to represent a bit. A bit can be turned into different things like bytes and terabytes, megabytes, which basically represents memory and things that we can store over time. Now that we've represented numbers, humans conventionally decided to use these numbers to represent letters as well. This is known as the ASCII system. For example, humans some ages ago decided that 65 in ASCII system would equal to the capital letter A. You would write the word high as 72 and 73 in binary to represent high in the ASCII system. Now that we can represent letters, we can also represent words. With words, we can represent sentences. And with sentences, we can represent paragraphs and paragraphs of things that we want to do with our computer. Now we can completely represent language with computers and binaries. But that's not all computers show. Computers also show color. And one conventional way that computers represent color is using something called an RGB system. An RGB system basically talks about how much red, how much green, and how much blue to combine to create a color. So 000 would equal to something like white because there's no color at all. And 256, 256, 256 would equal something like black because all the colors are combined together. In this way, we can represent various amounts of colors by just using 3 different numbers. And with tiny, tiny, tiny colors, we can represent images that are made out of pixels. We can create high-resolution pictures, and we can also create various types of videos. Now, after all of this, we once again come back to the problem of if computer science is the process of solving problems, then what is the thing in between, the black box that we haven't talked about? How does the computer take an input and magically take out an output? This black box is the heart and core of computer science and is known as something called algorithms. Algorithms are various sets of instructions for the computer to follow in order to convert that input into the desired output. Now, these algorithms are usually written in something called a programming language, but that doesn't mean humans cannot use this algorithm as well. That's why we have pseudocode. Pseudocode are sets of instructions that are written in human language, so it's for us to make it clear in our minds what we actually want to do. Usually, programmers use this to get a clear mindset of how their program is actually going to function before actually implementing it with a computer language and other things of sorts. But pseudocodes could be something like picking up this notebook and tossing it somewhere, or something like finding a name in the dictionary. And with pseudocodes, we can also see how there can be various competitive skills into the realm of computer science. Now, if I were to look at a dictionary, I could find the name, let's say, Abraham, either going through each page, page by page. That would take a long time. Or I could look at the problem by flipping 2 pages at a time and looking for Abraham at every other page. But this way we'd also miss a page in between. So this algorithm also might not work. Or you could create an effective solution to the problem where you cut the dictionary in half and take the right side of the dictionary and discard it, because we know Abraham comes before the middle part of the book, so you don't need the right side at all. Then you'd cut the left half of it into tinier pieces until you find the word that you're looking for, which is Abraham. Now, even though this is a pseudocode of how to find a solution, we can translate this into programming languages and it would be known as an algorithm of sorts.
If you like the content in this video, please like and subscribe for more content on this topic.